Okay, I did it.
Okay, good. Thank
Thank
you.
you.
Oh,
All right. Um, okay. Oops. That's not what I want. Okay. So we just quickly recapping what we said about knapsack. A typical knapsack problem. By the way, there are many variants of the knapsack problem. So here is a reasonably simple version, although there is one that's even simpler than this. In this version, we are given a set of n numbers, and we're asked, is there a combination that adds up to the number b? So we're given two things. One is a set of numbers and this number b, which is your target. And you're asked, is there a set of values, set of numbers from this from the set that you're given? Is there a subset that adds up to your target b? And here we are going to assume that n is reasonably large, and we can't really test out all possible subsets because the number of subsets are large, 2 to the n. And so trying to figure out whether they add up to b's can be a challenge. Now, by the way, this problem is, if the numbers are not integers, then we cannot come up with an approach like this. If they're all going to be real numbers, then it becomes way too challenging. In fact, it's known to be what is called as NP-hard problems, which means that you don't have very good solutions for them. They're all going to be exhaustive search. So you really have to do the 2 to the n subsets search. Okay. So now I'm going to just quickly recap what we did for the dynamic programming approach. So supposing you're given 5 items and their weights are what are given in the second column, 1, 2, 7, 6, and 5. The question is there something that adds up to the number 11? You can think of this as the knapsack problem, where the items have weights and you want to know which items I can pack in my backpack in such a way that the total weight is exactly 11. And we saw how we could do this by filling up this matrix below in blue. And the way we do this is we tackle this problem by starting with a simple version of the problem and then making it increasingly complex. At the start, we assume that we have nothing to choose from, in which case the decisions are easy. You know exactly what you can do if there are no items to pick from. The next thing you would do is to figure out what you can do with one item. If there's only one item to choose from, you only have 2 choices. Either you take it or you don't take it. And so you know exactly what the weight of the knapsack would be if you take it. You know exactly what is the weight if you don't take it. So it's either going to be 1 or 0 because the first item has weight 1. That's your first row. So in this new matrix, the blue matrix, every entry has a meaning. Every entry is either 0 or 1. If you look at the ith row and jth column, the columns correspond to the weight of the items you're picking, and the rows correspond to the sets you get to choose from. So if you're looking at the ith row, then you're saying you can pick any items from the set 1, 2, 3 up to I. You can't pick all the items, but you can choose from the items 1 through I. So in some sense, it's handling a simpler problem, namely, it's not trying to take all the items at the same time, but it's slowly, step by step, increasing the set of items you can choose from. And for each of these subsets, you go through an entire row that says, what are the values that I can achieve as a sum based on this set that I want to pick from? So if I only have one item, then of course I can only do a sum total of 1 or 0. These are my only 2 possibilities. So 0 is possible and 1 is possible. On the other hand, if I go to weight 2, then sorry, if I go to item, if I can choose from either 1 or 2, now it becomes more interesting because I can do 0 if I don't pick anything. I can do 1 if I only pick the first item, right? Because first item has weight 1. I can get only 2 if I only pick item 2, because item 2 has weight 2. And I can also achieve 3 if I take both of items 1 and 2, right? So it turns out all these will be 1, the rest will be 0 because I cannot achieve anything more. So what this tells me is that I can fill up knapsacks of size 0, 1, 2, or 3 all the way to capacity if I only have to pick from items 1 or 2. Now, there is a formula here that tells you exactly how this matrix has to be filled up. And that's what we wrote down here last time. I know I made some mistakes. I hope it's now corrected. Yeah, it seems corrected now. So it says that M of the, if I look at the jth row and kth column, I put in a 1 here if either it's 1 in the previous row for the same column, that's this guy here, jk minus 1, or it could be that in the previous row, I have to go some steps behind in order to figure out that it was 1. Okay, and by the way, this should have been j minus 1. So still there are some mistakes here. I think I corrected in some places and not in the others. So I go to the previous row, I check, I go back several columns. In fact, how many columns do I go? Remember, in the kth row, I only have one new item, and that is the item number k. Because in row k minus 1, I could choose from everything up to 1, 2, 3, all the way up to k minus 1. For the kth row, I only have one new item, and I really have only two choices. Either I add it or I don't. So what I'm going to do is I look at the previous row here, and I will know exactly how to fill this up because now I only have one new item, and that's the third item. And the third item has weight 7. So for each of these guys, I could add 7 to it or not add 7 to it. Those are going to be my only possibilities, and all those places are going to become 1. Did that make sense? So I know that in the previous row, I could fill up 0, 1, 2, or 3. So in the next row, I can fill up 7, 8, 9, or 10. Because from the choices before, I could achieve 0, 1, 2, or 3. And now I'll add the third item, which has weight 7, and that will make the weight as 0, 8, 9, or 10. Sorry, 7, 8, 9, or 10. And that's what happens here. You'll see that in the next row that we have put 0, 1, 2, 3, and then also 7, 8, 9, and 10. Did that make sense? So this 7, 8, 9, and 10, where it became 1, these happened because those guys were 1s, and the third item has weight 7. So I take the previous row values, add 7 to it, and those will be my new knapsack weight values. So here we're trying to figure out all the knapsack weight capacities I can fill up. So then for the next row, I only have one new item, and that's item number 4. And item number 4 has weight 6. So where would I have 1s now? Anyone wants to help me? So first of all, everything that's in the previous row gets transferred automatically because those were possible simply by not taking the 4th item, right? So if I don't take the 4th item, I will get 0, 1, 2, and 3, or 7, 8, 9, and 10. So those I know are possible knapsack capacities to fill. Now, because I have a new item whose weight is 6, what new values can I achieve? What new capacities can I fill?
4, 5,
help me with this? Go ahead.
4, 5, and 6.
How can I do 4?
Because you can take 4 alone.
Remember, the 4th item has weight 6. So 4 is not a weight 4. This is just the number, right? So item number one might be your laptop. Item number two might be what else? Well, no, let's not make item number one as laptop. Let's make item number one as your pen. Let's make item number two as your cell phone. Let's make item number three as your laptop. Let's make item number four as something else, a book, and let's make item number five as your wallet. So each one is a different item. Okay. Now what this says is I can only pick from one, which is your pen or pencil. In the second row, I can only pick pencil and your cell phone. In the third row, I can only pick pencil, cell phone, and laptop. I'm giving you one more choice there. And so in each row, I'm giving you one more item as a choice. So here, the fourth item is a book, and that book has weight 6. Okay. Now, if I didn't have the book, I can look up the previous row, and I know exactly what weight limits I can achieve. That is 0, 1, 2, 3, and then 7, 8, 9, and 10. Now, with that new book, which is a weight 6, what are the new weight values I can achieve? Well, if I don't pick up the book, I'll have exactly what I had before, right? Which would be 0, 1, 2, 3, and 7, 8, 9, and 10. Now, because I have the book, what can I do?
You can achieve weight 6.
So I can achieve 0 plus 6, or 1 plus 6, or 2 plus 6, or 3 plus 6. And then I cannot do 4 plus 6, 5 plus 6, 6 plus 6, because those were 0 in the previous row. But then I can do 7 plus 6, that's 13, 8 plus 6, that's 14, 9 plus 6, that's 15, and 10 plus 6, that's 16. Got that?
Got it.
So in the next row, if I had more columns, I would have those guys all filled up with ones. Is that clear? But because I'm only interested in a knapsack of weight limit 11, I've not even bothered to show you those columns.
Mhm.
Right?
Right.
So in the next row, I am going to, it's going to end up looking like this. The only thing that was new here was 6. All the other ones were over on the right-hand side. Is that clear?
Mm-hmm.
Okay. So now help me with the last row. What is going to have? What are we going to have here? Well, first of all, you're going to get all the things that are in the previous row, right? And then we're going to be able to add item 5, which in this case turns out to have weight also 5. So what new knapsack capacities can I achieve?
We can achieve 5 plus 0, 5
Correct.
plus
We can-
1, 5
That's right.
plus 2, 5 plus 3.
So it'll start from here, and you'll get 5 plus 0, 5 plus 1, 5 plus 2, and 5 plus 3. And then these two will remain because they were there in the previous rows. But then the next number would be
5 plus 6.
5 plus 6. That would be 11, which is the one we are interested in.
Yep.
Okay. So there you go. When you fill this up, you'll see that there's a 1 in column 11. And at this point, we're actually done, because our question was, can we fill knapsack of limit weight equals 11 with 2 capacity? And the answer, of course, is yes. Is that clear? So this is how these knapsack problems go. They are adding up things. Now, you could also do this with coins. Let's say that I have a penny, I have a nickel, I have a dime, and I have a quarter. And I want to know what are the different values I can make up with these 4 coins. So my first coin would have value. Instead of weight, I'm going to call it value now. So first coin makes value of 1. Second coin makes value of 5. That's the nickel. The third coin is a dime that makes a value of 10. The fourth one makes a value of 25. So now I can build up this matrix, and I will know exactly what are all the values I can make, right? And I know that the highest would be 25 plus 10 plus 5 plus 1, which is 41. So I'm never going to make anything more than 41, but I can create exact change of only certain values, not all values. I won't be able to do, let's say, 17, But I could do 26. I could do 27. No, sorry, not 27. I could do 30. I could do 31, things of that sort. So only some of those values are achievable with those 4 coins. Now, what if I have 1 penny? What if I have 3 pennies, 1 nickel, 2 dimes, and a quarter? Well, again, you would call each of those values appropriately and put them in that table, and you would fill up this table, and you will know exactly what values you can achieve. Okay. So I'm just giving you flavor of other kinds of questions you can solve using the same framework. There's nothing different. Just because it's called Knapsack doesn't mean it has to be Knapsack. It can be used in other contexts. Is that clear? So, so this is a general framework for solving many different problems. And the whole approach is called dynamic programming. And there are there's some stuff here that we need to know, but we'll come back to it, come back to this next semester. For now, let's put this aside. I'm going to say a little bit about the bad packing problem. Before that, I wanted to say something else, actually. Let's go back to this problem. There are other versions of this problem where let's say I have a third column. The first column says item, the second column says weight, and the third column says, let's say, its value. So remember, the first item is a pen. So let's say the cost is, its value is $5. The second item is a cell phone. Let's say its value is $600. The third item is a laptop. Let's say its value is, I don't know, $1,200. The fourth one was a book. Let's say it's $100. So now, along with the weight, I have a value associated with it. Okay. Now I'm going to ask a slightly different question that says, all right, I have a knapsack of weight limit 11. You can't take more than a limit of 11, but I want you to maximize the value for me. Okay. Or another way to think about this is, let's say that you are a cat burglar, and you go into Lazaro's house and you want to steal some things from his house. And he's got these valuable things sitting on his desk, and you have a knapsack to steal from, with which you can carry away the things in his house. Now, the knapsack, of course, has a capacity. You can't carry off more than what its capacity is, but your job is to maximize the value you steal from him. Okay, that's exactly the same problem, right? Mm-hmm. So our goal is to figure out, for a given capacity, how do we maximize the value? So now I'm going to now add a third column here called the value. And my question is not whether I can fill the knapsack to capacity. In fact, I might even have less than its capacity, but my goal is to maximize the value I steal. Does that make sense? So how do I do this? Well, one might think that because there's value involved, maybe I should start with the most valuable thing. Maybe I should steal the laptop first, right? But that doesn't always work out. What if the laptop were heavier than your limit? Or what if the laptop were so much that you couldn't take anything else? Okay. In that case, maybe it's better to take 2 lighter things whose value adds up to more than that of the laptop, right? So just being greedy and saying, hey, this is the most valuable thing here, let's put that into the knapsack, doesn't always work. So a greedy approach doesn't work. Even trying to be smarter and saying, let's find the maximum value per weight, okay, Even if you did that, it turns out it doesn't work. Okay, so it turns out that this dynamic programming approach is the only approach that works. Okay, now the question is, how do I modify my method to now account for the value of each item?
Okay. Not totally sure this is correct, but this is how I'm thinking of it. We still want to do the main question is still a knapsack question. So
yeah,
we want to initialize our 2D array, but instead of zeros with negative infinity,
okay,
and then instead of 1, maybe 0 or 1, but then we still want to carry out and see if we can hit that capacity, that weight capacity.
yeah.
Whereas we're selecting the ones, we want to do a maximum between what we're about to continue with or what we currently have.
Very good. So let's actually do an example. What I'm going to do is I am going to I'm going to use my whiteboard here. So let me first yeah, let me swap this screen here and see if I can. Huh. No, I'm not able to do this. Okay, let me get out of here and give me a couple minutes. So let me set this up. Yeah, so Lazaro is right. It turns out you can modify the approach we have to take care of the value. And let me show how this is done. So I am going to first go back and remove my background. All right, I'm going to use the whiteboard here. I don't know if you can, are you able to see this, you think? If I write, you see it?
We can see it, but it might be bigger if you stop screen sharing, so your camera is in the center.
Sorry, say that again.
If you stop screen sharing, your camera will be in the center. Yeah, there we go.
Okay. And all right. You all good?
All good?
Okay. Okay. All right. So we have, let's say we take 5 items. Let's call them items 1, 2, 3, 4, and 5, right? Let's give them a weight like before. I think we had 1, 2, 7, 6, 5. Let's keep those same weights. And let's put a value here. And I'm just going to make up some numbers just to use something here. So let's say we have 5, 1, 10, 4, and 6, just for the sake of argument. Yeah. And let's say we want a capacity of 11. Let's say we have a knapsack whose capacity is 11. So we already know that we want to build a table. And I'm just going to show you a little bit of how you do the calculation so that this works. So here's my table, right? So I am going to have several rows, of course. The first one is for the empty set, right? Can you see all that? The second one is just if I only take item 1, then if I choose from items 1 or 2, or items 1, 2, or 3, or 1, 2, 3, and 4, things of that sort. And then the last row will be to choose from all 5. Okay. Now, if I have nothing to choose from, it's easy. So by the way, I'm going to have columns with values 1, 2, 3, 4, 5, going all the way up to 11. So if my weight limit is oh, by the way, I need a column for 0 also, just to be just to make things clear. Now, the big difference is earlier I had this matrix with only zeros and ones. That simply told us, is this possible? Is this not possible? What I'm going to do now is, instead of just saying, is it possible or is it not possible? Instead, I'm going to put in what is the best value I can make. Okay. And remember, I don't have to fill it to capacity. It's okay if I fill it less than capacity. My goal is to maximize the value, right? So that's what I'm going to try and achieve. And so if my capacity is 0, my value is always going to be 0. And it's always possible. So I don't have to do anything here. This is just going to be 0. Okay. Now let's see if some other color works so that, oh, not very good. But we'll try this and see if this color works for you. So if I have nothing to choose from, all these are going to be just 0. Oh, that's horrible. All these are going to be just 0. All the way, right? If I have only one item to choose from, there are only 2 possibilities. Either you take it or you don't. If you take it, you're going to make weight of 1, but the value is going to be 5. So for weight of 1, I can achieve a value of 5. And everything else is going to be just 0. Sorry, everything is not just 0. In fact, everything else is just 5. Why is that?
Because we're trying to see, we're not trying to fill it all the way up. We're trying to see as much as we can.
As long as I have a capacity of 1 or more, I can take that item, I can steal this item, and I can achieve a value of 5. Correct?
Correct.
Any questions from the others? Adriana, Ernesto, David, is this all okay?
Yeah, we're good.
Okay, good. So now I have 1 or 2 I can choose from. So the second item has value only 1. And so how do I fill this up? What do you think is going to happen? Well, if I have a capacity of only 1, there is no way I can take item number 2 because its weight is 2 already. So therefore, I'm just going to copy this down here, because that's the best I can do. If I have 2, well, I have 2 choices. Either I can take what I did before, which means I don't bother to take the item 2, or I take item 2, in which case I cannot take anything else. And if I don't take anything else, the value is going to be
1.
1. So therefore, I'm going to pick the larger of 1 and 5, and it's clear that I'm better off just taking 5 instead. Is that clear? So I can fill it up, but I don't have to take item number 2. In fact, I'm going to choose not to, because my goal is to maximize the value. Fine? Thank you, Lazaro. So now you'll see that the rest of this row is also going to be 5.
Wait,
Fine.
what? For 3 and 4, wouldn't it be 6?
Oh, yeah, sorry.
You can take 1 and 2.
You're right. Thank you. I appreciate that. So this is going to be 6. By the way, once you reach a value, then if you go to the right, it can only increase. It can never decrease. Right? What happens then? Now I have the third item I could choose from, but its weight limit is 7. So it's not going to impact any of these. In fact, if I take that item, I can only, the weights I will get are either 7, 8, 9, or 10, right? So what are columns 7, 8, 9, and 10 going to look like? Well, by the way, out here, I'm going to have 5, 5, 6, 6, and then I'm going to have 6, 6, 6 for a while until it becomes
10, right?
It'll become 10 at which column?
7.
7, yeah.
At column number 7, exactly. So at column number 7, it'll be 10. And then at column number 11, it will be
16.
Actually, it'll be 15, right? For column number, column number 8. It'll be at column number 8. It'll be 10 plus 5.
15, yeah.
Column number 9, it'll be 10 plus 5. Column number 11, it'll be 10 plus 5 plus 1. Is that clear?
Mhm.
Now, it turns out we didn't do this randomly. We didn't go and figure this out. There is a simple formula for this. And that's what we're going to look at next. So here's the formula. Let me show you the formula. So earlier, the formula I used was the following. Can you still see me? Can you still see all of this?
Yes.
Okay, good. So let me look at this formula here. So the formula says mj of k is equal to, this is what we had before, okay? So I'm not doing it over for this, but I'm doing it for the previous version. The previous version said mj of k equals 1 if either m of j minus 1 k minus, k is 1. All that's saying is if in the same column previous row, if it was a 1, then I take that 1 down, right? Are you with me? I can't see you guys anymore. Yeah.
Yes.
Yeah, we're with you. We're
The second condition was if in the previous row, if I go back some columns, and if there is a 1 there, then that would be okay. If in the previous row that's j minus 1, but if I go to k minus the weight of the kth item equals 1. So that's what this says.
Professor,
Yeah, give me just a second. So this was my condition. Yeah.
why is it weight of k and not weight of j?
You're right. It should be weight of j. Sorry. You're absolutely right. Yeah. Thank you. So this says if in the previous row, if you go weight of j columns prior, if that is a 1, then I could throw in the jth item. Its weight would be exactly this difference, and I would achieve exactly weight k. Is that clear? This is what I had before.
We can also stay. We don't have to do j minus 1, right? Since if it is a 1 in j minus 1, it will be brought down. Can we just do j of k minus weight?
We can't because we don't know if we already used the jth item there.
Okay.
Right? So we have to be a little bit careful. So that's why it's safer to use j minus 1. All right. So now I'm going to tell you how to fill this guy here. Now there is also going to be a value associated with it. So let's figure out how to modify this. And let me erase something here and see if I can write it down. All right. So how does this work? I'm going to say m of jk. Instead of whether it's value 0 or 1, I'm going to say it's the larger of two things. Okay. And the first thing is whatever was in the same column, but in the previous row. Right? So I look at the same column, but in the previous row, whatever that value is, if that's the larger of the two things, then that's what I'm going to take. But I'm also going to compare this with something else. What is that? I'm going to go to the previous row, but I'm going to go left some number of columns. In fact, I'm going to go to the same item I looked at here. Is that clear? So I am going to then do j minus 1, k minus weight of j. But then I have to do something more.
Do we have to add the value?
I have to add the value of
The current item, or
value of j.
yeah, value J.
So I pick either this guy or this guy, whichever is larger. Did that make sense?
Yeah.
Yeah.
So if I did that here, I can pretty much figure out any entry in this matrix. And you can apply this properly and check that your calculations are correct. Excuse me. All those people who have been quiet, did you get that or did I lose you?
We're good.
Okay,
David said got it in the chat.
okay, sorry. Yeah, I can't see the chat right now. Thank you.
And so did Adriana. She said got it.
Yeah. Can you hold on? Let me see who this is calling me again.
Sure.
Okay. So the problem has gotten even more complicated here because there's value associated with the items, but still the basic structure did not change. We had to change a little bit up there, but we were able to solve the problem. That's the general idea here. If you have any questions, I'm happy to answer that. Otherwise, we're going to go to something called the bad packing problem, which is what you got in the competition. All right, so let me go back to sharing my screen. Okay. Are you seeing my split screen?
We're seeing it kind of like last time, where we can see the next slide.
Okay, so you're seeing the split screen. Then swap displays, yeah.
There
Good
we go.
now?
Yeah.
Okay. All right, so the bad packing problem is somewhat related to the knapsack packing problem. The only problem is here we want to know, we don't want to know how well we can pack, whether we can pack things up to capacity. We want to know how badly we can do. So we want to be as far away from the packing capacity, but it should be such that I can't add anything more. So in other words, it's saying here you're given a knapsack, you're given a bunch of objects, and each one has a weight associated with it. But like some people are really good packers and some people are not. We want to know, we're not interested in how you can do good packing. We want to know how bad someone can be at packing. So what we want to know is figure out the least capacity we can use. So the knapsack is being filled up as little as possible to the least capacity. To the least capacity, but you can't add anything more. Okay. So it's very similar to the knapsack problem, except that we're not interested in 0-1 answers. Instead, we want to know how close we can get to the limit, or really how far we can stay from the limit. And so it turns out, by the way, in the previous problem, we could have done our knapsack problem, even, the ordering of the items didn't matter. We could have done, we could have renumbered the items as 5, 4, 2, 3, 1, and it would have been just fine. So the ordering of items were not important, but this time it turns out the ordering of the items is somewhat important. And the reason turns out, well, the reason will become clear to you when you start to understand this a little bit more. Okay. So my first step is to go back to my knapsack approach, my knapsack problem. And instead of just looking at them as a bunch of items, I'm going to look at them as items of increasing weight. By the way, this time I don't have value. This is just weight. And then I'm going to ask more or less the same question, but I will modify it a little bit. And this time, instead of asking whether I can reach a limit or not, I'm going to ask, what is the worst I can do? Okay, what's the farthest I can go from for each of the rows? So every entry there in this matrix is not going to be a 0 or 1 that says, oh yeah, I can achieve weight 6 or weight 11 or whatever it is. Instead, I'm going to say, supposing I had a weight of 6, what's the worst I can do? What's the farthest I can be from 6 without being able to add anything more? Okay. So if that were so, let's see how to get this started. Again, we're going to start with zeros on the first row because the set is empty. I don't have anything to choose from. So obviously the weight for that for taking nothing is nothing. So the question is, how do I take the first row? Well, in the first row, either I take item number 1 or I don't. So that means if I have capacity 1, I have to take this item because I don't have a choice. As long as I can fill it, I should take it. Okay. It's just that if I have many choices, I'll try to pick a poor choice instead of a good choice. And so if I have weight capacity of 1, I should be able to take weight 1 and fill that up. If I have weight 2, again, I have only one item, so I have to take it. So really what you'll see is that the first row, the first row is going to give me, what did I do there? I made a mistake. So that shouldn't be a 2, that should be a 1 over here. That should say 1, because all I'm saying is, how can I fill it up by leaving the largest gap? Okay, and here it should be 1, not 2. So really, it becomes interesting in the next row. Let's see what we can do. Okay, well, not even in the next row. I think only in a couple of rows will it start to get interesting. Why did I put 2 here? I still have no idea.
Professor, I think the reason you did that is because of the output. You need to return an integer that represents the weight that you can fill it up.
Okay, got it. All right, so really what I'm putting in the matrix is not the worst I can achieve. Actually, I changed it, right? So let me restart here. Instead of putting the sorry, where did this go? Yeah, instead of putting in what is the worst, instead of putting in whether I can achieve the weight limit or not, or instead of putting in what's the worst I can do, instead of that, I'm going to put in what is the smallest numbered item that is missing in the knapsack. Okay, so that's why it says 2, because obviously I have to take 1. And the first thing that's missing is number 2. And remember, the items are sorted. So if 2 is missing, then 3, 4, 5, all the others are, well, all it says is number 2 is missing. But it also means that I cannot put 3 or 4 or 5 there. Okay. because they're sorted by weight. So therefore, 2 simply says that's the lowest thing I'm missing, but when I look at capacity 2, 3, 4, in fact, I should be saying the same thing here also. I don't know why I said 0, but anyways, that's not so critical. So let's move forward here. Now the question is, what is the next row going to look like? And you'll see that this is of course still 2 because it was 2 in the previous row. This here says, if I want to achieve a weight limit of 2, if I take item 2, then the smallest numbered item I'm missing is 1. If I take item 1, then I won't be able to put item number 2. So this should have been 2, not 1. Right. I did make a mistake here. So if you think about it, if my knapsack has capacity 2, I have the choice of taking 1 or 2 or both. But because the weight limit is only 2, let's say I were to choose to pick only 1. Then I won't be able to add 2 to it because my total would go over 2, right? So therefore, the smallest numbered item that's missing is 2, not 1. So that's why this is a mistake here. This should be a 2.
Wait,
Sorry
can you
about
say that again?
If my weight limit is 2, I have 2 choices. Obviously, I cannot take both because the weight would go beyond 2. I can either take 1 or 2. If I take 1, I won't be able to add 2 to it. So therefore, the smallest numbered missing item is number 2. On the other hand, if I take 2, the smallest numbered missing item would be 1. And of these, I will take the better, which is to fill it only up to 1 and have 2 missing. Remember, I don't want to fill it up to capacity. I'd like to fill it as badly as possible. So therefore, what I'd like to do is to pick the smallest. I want to pick the largest of the smallest item missing. And in this case, either I can miss 1 or I can miss 2. It's better to miss 2. Okay. So that's why this should be a 2, not a 1. Now, what about here? If my capacity is 3, well, I really don't have a choice. I have to take both of them. Okay, that means that the smallest missing item is the third item, which doesn't even exist there, but that's really what it is. Yeah, is that clear? Okay, let's see the next row. Hopefully it'll start to make sense to you. Yeah, again, I've made the same mistake with this guy here, but essentially it's copied from the previous row. Now let's see how we get these guys. Remember, the third item now has weight 5, not 7, right? So so if I look at the previous row, there was a 1 here for the 0th column. So I can add this item with weight 5, the third item with weight 5, and it will give me a 1 here, and it'll be a 1 here because I have now, the only thing in my knapsack is item number 3, whose weight is 5. So I cannot put anything more. So therefore, the lowest numbered item that's missing there is 1. Is that clear? Now, what happens if my capacity is 6? Well, I could do the following. I could add the third item and the first item. That would fill it up to capacity. I cannot put item number 2. So therefore, the first item it's missing is number 2. Now, what about 7? well, if it's 7, then I could again take the third item and the first item. So this should have been 2 again. I made a mistake here again. And that's because I made a mistake here. And so that's carried over here as well. This should be 2 because I could do the third item and the first item, and I would have a little gap of, I would not be taking the second item because I've already filled it up. Whereas if I look at column 8, I would have to take all 3 items, 5, 2, and 1. They would add up to 8. I filled it up to capacity, and the smallest numbered item that's missing is number 4. Now let's see how this is useful. It'll start to make sense in a couple of minutes. When I fill up the next row, that's what it looks like. And then I fill up the next row, and that's what it looks like. And what you'll see here is that if I have a weight of 11, the best I can do is to miss the first item, which means that because the first item had weight 1, I would be able to fill it up all the way up to 10 and leave a gap of 1. No, sorry, did I say that right? Yeah. Wait, did I say this right? Yeah. So it's because it's missing. Sorry, I actually got that wrong. W can be achieved by taking 5 and 6. And so therefore the smallest numbered item that's missing is number 1. So therefore there's no gap. You've filled it up to capacity. The question is, could we have done better? And it turns out that you can. So in order to actually get the right answer for what we can do in terms of leaving the largest gap is you don't take what you get over here. Instead, you work your way backwards and figure out which of these answers helps you. So it turns out that you could have filled it up to 10 and left a gap of, and the third item would be the smallest item missing. So that means that I could have taken that value instead, or I could have gone to 9, and that would have told me again that I'm missing number 3, which is a weight 5. Well, before we try and understand this, what do you think is the right answer? What is, if I have a knapsack of weight 11, of capacity 11, what do you think is the lowest I can fill it up to? Any thoughts on this?
So with a weight of 11,
yeah,
the lowest weight you can choose. So with the remaining, you can fill it up. Is that the question?
What is the lowest I can pack it up with? What's the worst packing I can do?
One.
If I did 1, then I could have added 2. There's space for 2. Then I would have to add it. So 1 won't work. If I so remember, whatever you do, your worst packing is defined in the following manner. You put in you come up to the least level, but you cannot add anything more. That's your worst packing. So this is like somebody who says, you give them a suitcase and you say, hey, put everything in here. And this person puts in a few things and says, no, there's no more space for anything else now. But they have not filled it to capacity. Instead, if they had rearranged it or put something else instead, they would be able to take more. So the question is, what's the worst packing you can do? So I know I have a knapsack of capacity 11. Obviously, I cannot get away with 1 because if I only fill it up to 1, then I still have 10 more left and I could take any of the other items, right? So that's not going to be, that's not going to fit our definition.
Is-
2 won't work, 3 won't work. What would work?
7.
If I take 7, then which one would I take? If I only take the item number 5, then I still have capacity. I still have 4 left over, and I could throw in any of the other items. So that won't be a packing. Packing has to be such that I cannot put anything more. So you need to tell me what's the worst I can do. Which item should I pick in order to make the worst packing?
Wouldn't the worst packing be 6 and then 5, and then you can't add anything
Take
more?
6 and 5. Of course, I cannot fit anymore. You're right in that I cannot add anymore. But now I have filled it to capacity.
Mhm. Oh, but you can't. Okay, so you can't fill it to capacity.
No, you can if that's all you can do. But remember, my goal is to make the worst packing.
Okay.
Is that the worst?
Worst.
Can I do 10? Can I do 10 and get away with it? And it turns out the answer is yes for 10. But then I would ask you, can you do 9? By the way, how can I do 10?
7 to 1.
7 to 1. Now, if I take 7 to 1, there's no space for 5 or 6, right?
Oh, I get it now.
Yeah.
Okay. Yeah.
So 7 to 1 is already poor because I didn't fill it to capacity. And you're going to go, hey, why didn't you fill it up to capacity, right?
Yeah.
Well, can I do worse?
Yeah. 9.
Can I do 9? Can I get away with 9?
Yeah.
How?
6 to 1.
6 to 1. Can I get away with 8?
No.
Yeah.
Right? Because with 8 and then the remainder would be 3. 8 is 6 and 2. You could add 1, right?
But I could do some other combination.
5 to 1.
Yeah, 5 to 1.
Yeah. So if I did 5 to 1, I can. It turns out that's the worst for 11. Did that make sense? Now, the reason 5 to 1 is a better answer than 6 to is because the lowest numbered item you're missing in 5 to 1 is the 4th item, whereas in 6 to it's the first item, right? So that's why the table was filled with those guys.
So that's why sorting is important here.
That's why sorting is important, and that's why filling up that table with the smallest item you're missing is also important. Now it turns out I can go down to the last row and work my way backwards and figure out where it is that's going to work for me. And what you'll see is, let's say I look at column 6. Okay. In column 6, last row, it says I am missing item number 2. But item number 2 is only a weight 2. So if I only filled it up to 6, and if I'm missing 2, I should be able to add 2 to it. That means I can get higher. That means that's not going to work. Forget it. So let's go and look at column 7. That still says it's missing number 2. Well, I only filled it up to 7, and I have missing number 2, which is a weight 2. So therefore, I can still fill it up because my capacity is 11. That doesn't work either. Let's go to number 8. That says I can fill it up to 8, but the first thing I'm missing is 4. So 4th item has weight 6. 8 plus 6 is 14, which is beyond my limit. So I'm safe. So therefore, I stop at 8. So therefore, the answer is 8. So essentially, I'm going to fill this table up, and then in the last row, I'm going to work my way backwards to see which is the right answer. Did this make sense to everyone? Clement, did I lose you?
Oh no.
It's not easy, so please ask questions. I'm not sure if I'm able to explain this maybe there's a better way to explain this. And if you ask questions, that might help me to answer it appropriately.
I mean, from what I got from it, it's like it's essentially finding like the smallest weight where you can't add any more items.
Yeah, but the problem is that I can achieve 8 in multiple ways. For
Mhm.
instance, I can achieve 8 by 7 and 1, 6 and 2, 5, 2, 1. All these achieve 8. Now, which one is the best? Well, if I did 7 and 1, the first thing that I'll be missing would be item 2. If I did 6 and 2, the first thing I'll be missing is item 1. If I take 5 to 1, the first thing I'll be missing is item 4. And so I like the last one best because it misses the largest item. Did that make sense?
Yeah, that makes sense. Actually, yeah.
So that's why if there are many ways to make up 8, right? I will pick the one that is missing the largest, smallest item. Was that confusing enough?
Yes.
Yes. Yeah.
Yeah.
So you can also see on the slide that I'm giving you a formula to figure this out. All right. We can go over this formula. It says G of JK. By the way, I'm calling this matrix as G instead of M. G of JK is either max of whatever was on the previous row, which of course I've written it wrong. I've written it as JK minus 1. It's actually J minus 1K, right? Or it's from the previous row, J minus 1, but K minus weight K. I want to take the larger of those two. Or I'm going to take the next item. If I have to take everything so far, then I'll pick K plus 1, which is what I did in some of those rows. I know you're staring at it, so
Yeah.
let me see if I can explain. Of course, this entry here, G of J minus 1K is the entry in the previous row.
Mm-hmm.
Okay, that says I can achieve this number, but I'd be missing this as my smallest possible item. Great. I may decide I don't like that if I can do better by looking at some other item where it's missing a larger item. So I'm going to look at J minus 1, but K minus weight K, which is what I did earlier, right? And that'll give me one answer. Now, if you think about 8, remember, let's look at 8 over here. Okay. How did I get this 4 here? Well, the previous row was a 0, so that didn't help me, right? Because I want larger numbers. Or I could have done where am I? So the third item has weight 5. So I'm going to look at 8 minus 5, that's 3. And this says you could miss the smallest item I'm missing is number 3. But then number 3 is what I'm adding here, right? So therefore, I'm not going to be missing 3 anymore. Instead, I have to up it. Okay, that's why I'm putting 4, because I can't just put 3 here. 3 is the last item I just added. So therefore, I have to increase it. So that's why I call it 4, which is out of that range.
Mm-hmm.
You can look at this guy here. This 6 came about, this 2 came about because the previous row was a 0. That didn't help me. Or 6 could also be reached by 5 plus 1. And so I go to column 1, which says, if I take this, the first thing I'm going to be missing is 2. So I put down 2. Now I couldn't put down 3 here because 3 was the one I added for this row. So this came about because I added 3 to it. And so if 3 is the smallest number missing, I cannot put down 3 there because that's already into the set. And so I have to make it 4. So that's what this last thing is. Or it could be k plus 1 if all the items 1, 2, 3 up to j are included. So if you're in row 3, and if you've added everything so far, then you better call that as 1 extra, 1 more. So by the way, it shouldn't be k plus 1, it should be j plus 1. So that was another mistake. Yeah. So there are a whole bunch of mistakes here. I'll fix this and I'm happy to send it to you when you're ready.
Professor,
Sorry?
for row 2, column 2.
Yeah, row 2, column 2. Yeah.
So that one was supposed to be a 2.
Yeah, that should be a 2 because let's go over this one more time. 2 comes from no, you're right. So that is 1. That 1 is correct, actually. Yeah. So by the way, these numbers come from, can we achieve that precise weight? And if we did, of all the choices, what's the smallest number item you're going to be missing? So it looks like maybe 1 is correct. Yeah, no, I think the 1 is correct. Sorry. Is that what you were going to say either as well?
Yeah.
So this is the bad knapsack problem. It's not so easy, but at least the basics come from the knapsack problem, which you have understood by now. And so you have to sit on top of it and try to understand how to now navigate the question in such a way that you can answer it. So in all these problems, what you will see is that you create this matrix just like in the basic problem, but often instead of just putting in zeros or ones, you may have to put in some other new information. And that new information will help you to solve the problem you want. Now, in a previous problem, we also had value. And when value was involved, this table had values written in it. Whereas here, we're not using value. Instead, we're trying to keep track of the smallest item that's missing from our best selections. Or rather, our worst selections, right? I mean, we're doing worst packing. So we're saying, what is the smallest numbered item? What is the smallest item you're missing in your worst packing? Now, if that number is made as large as possible, then we know that in many cases, it'll help us to figure out whether some weight limit can be achieved or not. So sorry, it was a bit confusing, but really this is, it's very hard to explain this. And you really have to kind of get that intuition in order to make this work. So I am going to more or less stop here, but we should talk about what the plans are for. This is the last session for the semester. The other problems in the competition are a little bit harder. We would need to know more techniques before we try to solve them. And so the next semester, or rather when we start to meet again, we'll talk about graph algorithms. And we'll talk a little bit more about dynamic programming, because dynamic programming is actually much more interesting. And once you know dynamic programming, you can solve a heck of a lot of different problems. Okay. So we're going to talk about that. The question is when. And what I had suggested to Lazaro was that we should meet over summer, because in fall, again, we will have a competition and I would like you guys to shine. So we'll meet over summer, and I hope that you guys will be able to join. And he has sent you some choices for the time. So please help us figure out what's the best time. And Lazaro, were you able to find somebody who could start to take over from you? You said that you might not be able to join us or was that for fall? I can't remember.
What do you mean by join us for next semester?
Yeah.
No, yeah, I'll still be here,
You'll
but
yeah.
but
But
instead
there's
of
someone else who's doing the some of this management.
yeah, I'm not gonna be the vice president anymore. I'm gonna be competitive programming tech lead
Okay. All right. Got it. Now I got it.
if I get it first.
Okay. Excellent. All right. So let's continue to meet. Now, what I want to know is how many of you solved any of the problems from the competition after we've talked here? So uh, uh, I don't want to call on you, but I know you haven't really solved a whole lot of problems. So you guys need to do this because that's the only way you're going to get better at this. Just listening to me here is not going to cut it for you. I can tell you that. Because there's a ton of details, and some of you who have tried to take what you've learned here and go back and code this know the challenges. It's not that easy. There are lots of subtleties that are involved that you learn only when you get down to the programming. So it's not enough to get these lectures here. You have to go and try it. Okay. And I know you're busy now, but come summer, you've got to devote some time for this. Otherwise, just attending these lectures are not going to be enough to make you a crack shot programmer. Okay. So if you want to be working for the Googles and the Amazons of the world, and if you want to be working with cutting edge technology and programming and software engineering and algorithms, you need to spend some time now. All right. It's definitely worth it for you. So I would encourage you to come back and join us. I have arranged for you to get scholarships for the time you have spent this semester, and that will continue if you spend the time and if you spend the energy and if you commit to working with us. I will make sure that you're rewarded. Okay. But if you're not consistent and if you don't really participate, then I can't with good conscience arrange for scholarships for you. Fair enough? Questions?
So I guess over the summer we'll just be continuing with everything from like where we left off.
More or less, yeah. There may be some newcomers, but hey, they'll have to kind of catch up with us and work harder.
Yeah.
What I'll do is I'll start a new topic. In fact, I will start on graph algorithms. That's what I'll do for summer. So that's an important topic. You don't want to miss this.
Okay.
Okay. It will help you for data structures. It'll help you for a bunch of other courses. And of course, you already know it's an important topic. So come back and work with us. Adriana, you had a question?
Professor, around what time will we meet up again if we're not going to be doing the summer, not the summer, but we're not going to be doing the classes weekly after today?
Yeah, Adriana, that's what Lazaro is trying to help you figure out. So once we figure out a time, we'll announce it, and you will get some email telling you about how we're going to do the meetings for the summer. For fall, remember we're going back to 3:30 on Thursday. That's fixed in time. So make sure you keep it free. Okay, that's for your programming competition training. So keep that fixed. Let's not change it because too many people will get impacted by it.
And for fall, I know where some of us going back in person. Are you?
Yeah.
Yeah. Okay. Cool.
Yeah,
Awesome.
I'll
And
be
do you,
vaccinated and ready to go.
do you have your own room, or are we gonna have to set that up, the club?
Yeah, I will arrange for all that. Yeah.
Okay. Okay.
Yeah. Previously, we used to meet in room 235 on the second floor. If that doesn't work, I'm sure I can find other rooms. Yeah. Shouldn't be a problem. There are conference rooms. There's the room 235 Computer science has some other rooms as well, so we should be okay. One of those will work out. If not, we'll walk across to PG6. There are a bunch of rooms.
I've never physically been on campus, so like, is there a way to schedule a tour for FIU?
Sorry, say that again.
So I started FIU in the fall, but we were already in like, you know, COVID time, so like I mean quarantine.
In fall, pretty much all of you should be vaccinated. At least that's the expectation. FIU is already arranging for it so that all students will have access to vaccinations starting from next week. Even if you delay this for whatever reasons you might have, my guess is that by the end of summer, all of you should be vaccinated.
Wait, no.
The question really is, will we still have some online things? Well,
No, not that. My question is that I've never been on campus since I started. So like, does FIU offer tours or like an orientation or whatever for like getting to know the campus and stuff?
Yes, I'm sure there are. I've seen that before, but I have no idea whom you should contact for that. Maybe the student clubs could lead you, point you in the right direction. I know there are orientation groups. In fact, usually they do that late summer for students coming in for fall. So yeah, I'd say just do a Google search. I'm sure you'll find something. Yeah, looks like Lazaro has sent you a little. Yeah. Anything else?
Can we
All right.
still?
So, how many of you think you will be regular over summer? Because if the number is not so large, I'm not anxious to spend my energy. I see at least 2 hands up. Are there others who are planning to hang with us?
I would for sure.
David said he'll be there.
David
so-
said yes. Okay, good. Yeah. Anybody else? So,
Ernesto said yes as well.
oh, good. Okay. All right. Remember, you know, I need numbers in order to make my energy worthwhile. I am spending a fair bit of time here, so make sure you're there. Okay. All right, guys. Good luck with your exams, and we'll see you early summer.
Sounds good.
Probably late April or early May is when we'll start again.
Enjoy your trip.
Thank you.
Thank you, Professor.
Thank you, Professor.
Take care.